This video covers chapter 5.5.1 in the OCR A-level physics spec, so it's all of these topics. If you're looking at this list and you don't find anything you need to learn, then unfortunately this video is not the one for you. But if you do A-level OCR physics, or I think probably any A-level physics, and GCSE physics, then you're gonna want to know about these stuff about stars. Anyway, let's just get straight into it. So, first we gotta get into some terminology, so a bunch of definitions. So, we can define a planet with three criterias. Firstly, the object needs to have mass sufficient enough for the gravity to force them into a spherical shape. So, let's say the planet looks something like this, then, well, it's not considered a planet. Which is kind of a good thing, because if you think the Earth is flat, then I wouldn't want to live on the same planet as you. The second requirement for a planet is that it must orbit a star. So in our case, the only star that's nearby us is the Sun. And the third requirement is it must have cleared its orbit of debris. So, you know, when a planet is orbiting the Sun in this case, there's going to be like just rocks and debris in its orbit. And if it hasn't cleared its orbit, then it's not considered a planet. And this is actually the reason why Pluto isn't a planet, because it hasn't cleared its orbit of debris. Instead, Pluto is considered a dwarf planet, which a dwarf planet is just a planet which hasn't cleared its orbit of debris, which is pretty simple. Anyway, let's talk about some more words. Planetary satellites are just bodies that orbit a planet. For example, the moon. Comets are small, irregularly sized balls of rock, dust, and ice that orbit the sun in an eccentric elliptical orbit. The solar system is just the systems containing stars and orbiting planets. So our solar system has the sun and, you know, the planets Mars, Jupiter, Saturn, and Earth, obviously. The galaxy is a collection of stars, dust, and gas. So we live in the Milky Way galaxy, and I think the closest galaxy to us is the Andromeda galaxy. And I'm sure there's other galaxies, but I don't know any of the names. The last thing we need to know about is the universe, which is basically everything you can think of. It's all just classified as being inside the universe. And supposedly the universe is expanding. But I'm not too sure about this last point. I'm still waiting for the video proof. Anyway, let's talk about how a star is formed. So, in the universe, there's just a bunch of gas and dust, and this is called nebula. So it's basically just clouds of dust and gas that's in space, just floating around. And each particle in this cloud of dust and gas has a small gravitational force. And where the nebula is more tightly packed is where there's a higher gravitational force. So more and more nebula is just gonna group up in this one concentrated spot until you get so much that a protostar forms. And a protostar is basically just a high concentration of nebula in one place where the center gets really, really hot. And this disk around it is basically just nebula that hasn't been consumed yet. And it's actually called an accretion disk. So it's a ring around the protostar made up of nebula that hasn't been consumed yet. And so after the protostar stage, we get what's called a main sequence star, which has a pretty strong gravitational force, or gravitational field, and quite a high density. So our current sun is what's considered a main sequence star, and a main sequence star is also considered stable. And that's because the gravitational force that points towards the center of the star is cancelled out by a force that points away from the center. And this force is called the radiation pressure. And this radiation pressure is caused by nuclear fusion that happens within the core of a star. So basically, nuclear fusion is when two hydrogen atoms fuse together through conditions of very high temperature and a very high pressure. The high pressure is caused by the strong gravitational field. But basically, the two hydrogen atoms fuse to make a helium atom, and in that reaction, or in that process, it creates a large amount of energy. And this energy is in the form of electromagnetic waves, and this electromagnetic wave points away from the core. So it counteracts the force of gravity, and this is called radiation pressure. So it's the force that points away from the core and is caused by nuclear fusion. So that's why a main sequence star is considered stable, because we've got forces that are balanced. Now let's talk about low mass stars. So OCR considers the Sun to be a low mass star, but there isn't really a globally accepted requirement for stars to be considered low mass. Usually when we're describing the mass of stars, we're talking in terms of solar masses, which is its own unit where one solar mass is the mass of our Sun. So the mass of all the other stars in the universe is described relative to the mass of our Sun. So anyway, what I'm about to describe is the life cycle of a low mass star. So this is the life cycle that our current Sun is expected to go through. Basically, as I described previously, the core of a main sequence star has a bunch of hydrogen. And because it's such a high temperature and there's so much pressure from gravity, the hydrogen undergoes nuclear fusion. But it's not like there's an infinite amount of hydrogen. So when all the hydrogen is used up and is all turned into helium, the star can no longer undergo nuclear fusion. And so basically what happens is that the core starts to collapse under itself, while the outer layers of the Sun expand out. And the star becomes red. And this stage is called a red giant. And it's basically and you can basically think of it as a dying star. The star is basically dying, and the outer layers of the dying star will spit out nebula into space. And this is called planetary nebula. And even though the name has planetary in it, it has nothing to do with planets. And it's basically just the nebula that's emitted from a dying star. So another thing that happens in this stage is that the core continues to collapse under itself. And that causes the temperature to increase and the pressure to increase, because the core is so dense now. And this allows for nuclear fusion to happen with helium, which allows the star to create heavier elements like oxygen and carbon. But that means that once all the helium runs out, nuclear fusion stops again, and so there's no more radiation pressure. So the core continues to collapse on itself, and it heats up, until it eventually becomes a white dwarf. And some properties of white dwarfs are that they're very hot, and they're very dense. This means that they have a very strong gravitational force that points towards the core of the white dwarf. But the reason it doesn't collapse under itself even further is because of something called the electron degenerate pressure. And this is caused as two electrons cannot occupy the same space. The basic idea is that because the force of gravity is so strong towards the core, the electrons start pushing against each other. And this is in the direction of away from the core, because gravity is pushing the electrons towards the core. And so these two forces balance out, causing the star to be stable. So that's the reason why the star doesn't collapse under itself. And another thing you need to know about white dwarfs is something called the Chandrasekhar limit. I hope I said that right. But it's basically the largest possible mass for a white dwarf to be, which is 1.4 solar masses. And remember, one solar mass is the mass of the Sun. The reason why a white dwarf can't have a mass greater than 1.4 solar masses is because if it did, the force of gravity would be stronger than the electron pressure that points outwards from the center. So the star would just collapse under itself because gravity is so strong. And after that, the star would explode. And this is what's called a supernova. But we'll get into that when we're talking about massive stars. So typically a massive star, or a massive main sequence star, is usually blue. And the life cycle of a massive star is quite similar to the life cycle of a low mass star during the beginning stages. So just like with the low mass star, all the hydrogen in the core is used up, and that causes the core to collapse, while the outer layers expand to form a red supergiant. So the difference here is that because the star is so massive, the core heats up to higher temperatures, and also there's a higher pressure than if it was a low mass star. And this causes nuclear fusion of heavier elements to occur. All of this is happening while the radiation pressure and electron degeneracy pressure prevents collapse. So fusion continues until iron is formed, until the core collapses again, because, well, once nuclear fusion no longer occurs in the core, radiation pressure no longer counteracts the force of gravity. And in this case, because the star is so massive, the electron pressure is not enough to prevent collapse. So once the star actually collapses, the star explodes and the outer shell releases a huge amount of energy. And this phenomenon is called a supernova, which is basically when a star explodes at its last breath, because the star is basically dying. So the outer shell just explodes into space and probably becomes planetary nebula, while the core remains. And the core that's left over is what's called a neutron star. So a couple things about neutron stars. Neutron stars are very small and super dense. They also rotate rapidly and emit electromagnetic waves impulses. And this electromagnetic waves impulses is actually what allowed us to discover neutron stars. Another thing is that they have a very large magnetic field. One last thing to know about is that during the red supergiant stage, just before it explodes, or just before the supernova occurs, if the mass of the core is greater than 3 solar masses, then the neutron star would collapse under itself because the force of gravity is so strong, and that collapse would create a black hole. And I'm sure we all know what a black hole is, but you just need to know that some properties of black holes is that it's so dense that light cannot escape its gravitational field. This is something OCR wants you to know about, just properties of neutron stars and black holes. The last thing in this chapter is the Hertzsprung-Russell diagram, which is basically just a diagram of temperature measured against luminosity for stars. So white dwarfs are very hot. They're around like 30,000 kelvins, but they also emit the lowest light. Main sequence stars are between white dwarfs and supergiants and giants, whereas supergiants and giants are very, well, they're not low in temperature because it's still like 5,000 kelvins, but they're lower than main sequence stars and white dwarfs. And they also emit high amounts of light. So luminosity is just a measure of light. You do need to know about this diagram, so you need to know white dwarfs are around this area, main sequence stars around this area, and giants and supergiants are at the top right. They can ask exam questions about this. Anyway, that's the end of the video.